Alright, this is Chapter 3, Section 2. This is the second video. So last time we did independence and dependence. Now we're going to do mutual exclusivity. So independence has to do with multiplication, and mutual exclusivity has to do with addition. Okay? So two events that cannot occur at the same time are mutually exclusive. If they can occur at the same time, they're not mutually exclusive. Meaning you can be the same, you can be two of the same thing at the same time, right? So you can be tall and good looking at the same time. So those are not mutually exclusive, right? Okay. So when you do additive scenarios, you have to worry about mutual exclusivity. When you're doing multiplication scenarios, you worry about independence, essentially. So either way, the area is 1. So you'll see the words disjoint and joint, or disjoint and not disjoint, basically. And people think those are interchangeable with the mutual exclusivity. That has to do with the Venn diagram, right? Because either way, these are mutually exclusive, right? Because they are disjoint, right? I can be one or the other, I can't be both. This is not mutually exclusive, right? The Venn diagrams, in this case, are not disjoint. Right? Not disjoint, because they're not mutually exclusive. Because I can be both A and B at the same time, right? So let's say this is being tall, and this is being good looking, right? Some people are both, aren't they? Correct? Like myself. Say, but here you might not be both. You can be an apple or you can be a banana, but you can't be both unless you make some kind of weird hybrid species, right? So out here essentially is the probability of not A and not B. Right? So all you can be is an apple, a banana, or neither, right? Which is all the other fruits, essentially, assuming that the total area is fruit. So over here, you're tall and good looking, correct? Here is just good looking, but not tall. Here is tall, but not good looking, right? So good looking and not tall is over here, right? This is tall and not good looking, right? And this is both tall and good looking. And over here, right, because it's both, here would be, right, not tall and not good looking, correct? Right? Okay, so let's think of some scenarios here about mutual exclusivity, right? You're talking about single events, right? Whereas independence is talking about more than one event. Does one depend on the other? So if I draw a card, can it both be a king and a diamond? Yes, it can. You can get a king of diamonds. You can be both at the same time. So those are not mutually exclusive. However, okay, let's say you draw a card and you get can it be a face card and a 10? No, you can be a face card or a 10. Remember, a face card is the royalty, which is Jack, Queen, King, right? So that is mutually exclusive. You can be one or the other. Can a student be a female and a student be enrolled in Providence Stats at the same time? Yes, they can. So that's not mutually exclusive. You can be both. Being a Republican in New Hampshire, being a Democrat in New Hampshire. Well, those are mutually exclusive. I had to put New Hampshire because other states have weird rules, but you can be one or the other. You can't be both, essentially. You can be neither, right? You can be neither. That's a possibility, right? You can be neither, which is the outside, but the two things we're talking about are mutually exclusive, though. Okay? All right. So there were 3 rules for independence, right? You proved independence, right? 3 different ways, and you only had to prove one of them, right? You don't prove dependence because there's infinite ways one event can be dependent to the next event, right? You're talking about 2 different events, right? So you don't prove dependence because there's infinite ways you can be dependent, right? Mutual exclusivity, you do not prove not mutually exclusive. As to how they overlap, you don't know. That's infinite ways you can overlap. You can be 2 things or 3 things at the same time. There's infinite ways that could happen. All you have to prove is that they're mutually exclusive, which is simple. Is the overlap 0? Right? So is the overlap of Democrat and Republican 0? Can you be both? No, you cannot. Can you be a face card and a 10 and a deck of cards? No, you cannot. There is no overlap, essentially. All right, so let's think about this on a very small level. So either way, I have the same sample space of 1 through 10. So A here is 1 through 5, B is 4 through 8. So they have 4 and 5 in common, right? Here, you have the odds and the evens. They have nothing in common, correct? So these have nothing in common. These are mutually exclusive. These have something in common. They're not mutually exclusive, right? So essentially, sets A and B here on the first one is 4 and 5. The overlap is 2 out of 10. They have 4 and 5 in common, right? 4 and 5 in common. That's 2 numbers out of 10 numbers. So that's not mutually exclusive because clearly not 0, right? However, if you do this one, okay, if you do the overlap of A and B, right, using the formal rule, okay, you get the empty sets. This is the empty set symbol here, right? So make sure you use that. Don't just put nothing. They have nothing in common, so that's obviously 0, which means they're mutually exclusive, right? It can be one or the other. But those are simple numeric examples. We did some other ones up here that were not numeric. But okay, let's do some problems where we might have to apply some of this stuff essentially. Okay. All right, so we're going to do the probability of at least one, and we'll do more of this in some later chapters too. We'll do at least, at most, no more than, just different variations of that. Because whenever you use any of those type wordings, those are not asking for one probability. These are asking for more than one probability. So the probability of at least one means you get at least one of a specific event. Okay, which means you could get 2, 3, 4, 5, 6, 7. So again, those are multiple probabilities. Okay. The problem with those is they could be complicated to impossible to calculate. So what we're going to use is the complement method, which is when you use P of not A, right? So essentially, if we declare A as at least 1, right, then not A is having none of some event, right? Because none and some have to add up to 100%. Either you have none or you have some. That's the only possibilities, and some means 1 or more, essentially. Okay. So let's do a few examples here. So you draw 3 cards from an ordinary deck without replacement. Determine the probability of getting at least 1 heart. Okay. So the probability of at least 1 heart equals, okay. So the problem with this is that means I have to figure out the probability of 1 heart, 2 hearts, and 3 hearts. And if it was more than that, 4 hearts, 5 hearts, 6 hearts, but I don't want to do that. That's the direct way of doing it. So 1 minus the probability of no hearts is the indirect way of doing it. Okay, so let's make this blue. Format, color, blue. So this is the direct way of figuring it out. This is the indirect way of figuring it out. So the indirect way tends to be easier in a lot of cases. In a lot of cases, the direct way is not. So if you went to infinity, you can't figure out at least 1 because it's an infinite number of possibilities. So you'd have to figure out at least 1, 2, 3, 4, 5, all the way up to infinity. You can't do that. But the indirect case, which is the flip, does actually work. So 1 minus, and we'll do a bracket, and then fraction times a fraction times a fraction. Okay. So we're drawing a heart from a deck of cards, right? There are 52 cards in a deck, and there are 13 hearts, correct? But that's not what we're doing. We're doing no heart, right? Because there's, again, 13 hearts, 13 clubs, 13 spades, 13 diamonds. So not getting a heart is 39. But these are dependent events, right? These are dependent events, right? Because this draw depends on the previous draw. This draw depends on the 2 previous draws, correct? So this one is 38 out of 51 because there's 51 cards left. I already took a non-heart out, so there's 1 less non-heart. So the next one is 37 out of 50, right? So I took a non-heart, a non-heart, and a non-heart, and the deck keeps getting smaller every time, and there's fewer non-heart cards, basically. Okay, equals. So fraction minus fraction. So if you multiply 52, 51, and 50, you're going to get 132,600. That number comes up a lot if you do card stuff. If you multiply those on top, you get 54,834, right? So typically you want to have common denominators and least common denominators and all that. So two things. Your grade school teacher told you to simplify fractions. You don't need to do that, and that probably just makes things harder in probability, so just don't do it. And you do not need the least common denominator. All you need is a common denominator. So why can't I just use the one that I already have, right? So I'll do copy, paste, paste, because that's 1, isn't it? And that's 1. So instead of spending all day trying to figure out the least common denominator, just do a common denominator. It still gives you the same answer. Okay, so you put that on the bottom. So that minus that is going to be 77,766. Okay, can I simplify that fraction? Sure. Simplifying fractions is a guideline, not a rule, and you can convert to a decimal too if you want, but that's not absolutely necessary. Okay. Okay, so let's look at the DVD one here. So if I do the DVD one here, I'm buying a pack of DVDs which has 50 DVDs in it. The probability of a single disc being defective is 0.05. Thus, the probability of the disc being good is 99.5%. So determine the probability that at least one DVD in the package of 50 is defective. So we need the probability of at least one bad disc, right? Bad disc. Okay. But I don't want to do that because that would be difficult, very difficult to calculate. Because I would have to calculate the probability of 1 disc being bad, 2 discs being bad, 3 discs being bad, 4 discs being bad, all the way up to 50 discs. That's a lot of probabilities to calculate. I don't want to do that. It'll be much easier to do 1 minus the probability of no bad discs. Okay, so the indirect method is significantly easier in this case. The previous problem you probably could have done either way successfully, but this one is very difficult to do directly. Indirectly is much easier. So 1 minus, okay, does one disk affect the other disk? No, it doesn't. So these are independent events, right? So one disk does not affect the probability of the other disk, whereas before, drawing a card affected the next card, didn't it? So it's independent. So it's 0.995, because again, we're not looking for a bad disk anymore. We're looking for no bad disks, right? So this, in parentheses, to the power of 50, right? So I don't need to list this out 50 times because it's the same number every time because they're independent, right? And if I plug this into the calculator, it's not going to work out nicely, which is fine. Just go out at least, 4 decimal places. So 0.221687, right? So always go out at least 4 decimal places in probability, okay? Unless it's one that there's a lot of zeros, you might need to go farther, but that's generally pretty good. Okay, so there's decimal scenarios and fraction scenarios. There's dependent scenarios. There's independent scenarios. Okay, let's look at a couple more. So let's say we want to look at birthdays in September, right? So we're going to have at least one person born in September out of 3. So we need the probability of at least 1 September. How's that? Okay, so at least 1 September. But I want to do it indirectly, so 1 minus the probability of no September, right? Okay, so equals 1 minus, we'll make this blue. Okay, so let's think about this for a minute. Does your birthday somehow affect somebody else's birthday? Well, again, we're going to assume you're not like siblings or twins or anything like that. So we're going to say they're independent events for the most part, right? We're not going to assume any weird scenarios of twins or being related or anything like that. You know what I'm saying? So your birthday has no effect on somebody other stranger's birthday, essentially, right? Okay, so we got to put a fraction here. So we're going not a September birthday, correct? So that's 11 out of 12, right? Because we want to know September birthday, so we're doing the flip, which is 1 minus not September, right? And we're doing how many people? You pick 3 random people. I don't know why I kept doing 3. I'm not sure. Probably should change that, right? Okay, so it's going to be fraction minus fraction. So if I do 11 to the 3rd, that's 1331. If I do 12 to the 3rd, that's 1728. So same thing. Don't simplify fractions and don't find least common denominators. Just do a common denominator. Make it easier for yourself, right? So I don't have to reinvent the wheel here. So I'm going to get This minus this would be 397, and that's 1728. Okay. Can you simplify that fraction? Sure. Can you get a decimal for that? Sure. Is it necessary? No, not really. Okay. So, according to the Necktie Association, 3% of the U.S. population has purchased a necktie in the last year. Determine the probability of picking 3 random people from the U.S. population, and at least one of them purchased a tie in the last year. Okay, so you're reading this, you're like, well, this is a dependent scenario, because if I take a person out of the population, there's one less. That's going to change the probability of the next person. Yes, that's true, but whenever you're doing a population model, taking one person out of the population matters so little when you're doing a small sample that you're actually going to treat it as an independent scenario. Okay? So, whoops. What I want to do here is, instead of doing at least one tie, do the 1 minus probability of no purchase, right? So 97. So if it's 3% purchase, and it's 97 did not purchase, which is approximately a decimal. And again, I'm treating this, since it's the same one every time, I'm treating this as independent, even though it really is dependent. But it's so little difference, it doesn't actually matter, because you take one person out of, or 3 people in this case, out of 400 million people, it's not going to matter all that much, to be honest. Okay, that's the end of this part.